Next, we know that it's in a fixed location on the sky. So if you can show that a signal is coming from a fixed source in the sky, then it's also indicates that this might actually be from that source and not from a local source. So one of the ways, which I'll speak a little bit more about later on in this presentation, is one of the ways of determining this is by, if you have a single dish antenna, you can point it at the object of interest, record, and then point away, and then point back on the object and take a look at the signals that you receive on and off pointings. And this is exactly what's been done here. And you can see that the signal does not appear in the off pointing, which provides evidence that the signal may actually, in fact, be coming from the source. There are other ways of doing this, which I'll speak about as well, but this is what was possible here. So that's another characteristic of interest. Another important thing to look for is drift in frequency. So all signals where the transmitter is accelerating relative to the receiver will show a drift in frequency over time, which is what one sees here. And if this drift is adheres to certain characteristics and is linear in some cases, or not necessarily linear, but smoothly varying, then it could be consistent with what you might expect from an orbital environment or rotational environment, such as if a transmitter were located in orbit on the surface of a planet, for example. And then another characteristic is persistence. You can see the signal appears across multiple pointings and for a relatively long period of time. So these are some of the characteristics that we might look for. Although this is not an exhaustive list, of course, these are just some characteristics that might indicate that the signal is of particular interest. I should mention that the full analysis is available in this paper, which you can look for online. Ultimately, with further investigation, it was determined that the signal is radio frequency interference. So even though a signal might exhibit these different characteristics that I've mentioned, it's by no means a guarantee that further investigation won't yield other information that might point in one direction or another. So next, I'd like to just speak a little bit about SETI with single dishes. So single dish telescopes, such as Green Bank, or the telescope in Australia, Parkes on the right. These are large single dish telescopes which are very sensitive. And as I mentioned before, an on-off observing cadence is how one would look for sky location on the sky. So on the left is an example of another observation that was taken from a different publication, where you point the telescope at the source and then you point off source on a different object or a random region of sky, and then back on source and so on. And if you see the signal in the off source pointings, it's most likely to be radio frequency interference, because if it's nearby, the signal could be getting into the telescope through the side lobes. So single dish telescopes, while they're very sensitive in a particular forward facing region in the focus, they also are, since they're so sensitive, they can also receive signals from other angles, from the sides. And since our radio frequency interference from nearby sources is often very powerful relative to astronomical sources, it's still detectable, even though it's entering in a non-sensitive region of the telescope's beam pattern. Next, I'll speak a little bit about SETI with array radio telescopes. So on the top left, you can see MeerKAT. I'll speak a little bit more about MeerKAT shortly. On the bottom left is the Allen telescope array, and to the right is the very large array. And I've drawn a small diagram on the right, which I'll speak a little bit more about next. But one of the important considerations here is that array radio telescopes require much more computation than single dishes. So the way that radio signals can be received with array radio telescopes is by summing the signals from all the individual dishes together to form a more powerful or a signal with better signal to noise ratio than would be received by a single dish. But because the dishes are located in different places, the signals from astronomical objects arrive at the dishes at slightly different times. And so in order to get a clear signal, you have to either provide delays or phase offsets so that the signals all arrive together and are summed correctly. So in this example, you can see those lines represent a sort of a planar wavefront that arrives at the right-hand antenna first before the second antenna. And so in order to get the correct part of the signal to sum with the signal received by the second dish, you'd have to apply a phase offsets or delays. The other thing that can be done here is electronically steered beams. So let's see. So this slide illustrates beamforming. So your individual small dishes have a field of view, that area of the sky that they're sensitive to. But if you have multiple of these dishes, you can use this beamforming technique to sum the signals from different places within the primary field of view. And so you can have multiple electronically steered beams on different objects. And this has important implications for commensal observing, which I'll speak a little bit about in subsequent slides. Another mode of observation, I'll just mention this briefly, is the incoherent sum. So instead of creating these steered beams, one can just look at the entire field of view altogether. So the disadvantage of this is that the sensitivity is reduced by a factor of the square root of the number of antennas when compared with coherent beamforming. But you get the full field of view, which is, in the case of MeerKAT, about 1 square degree, which is a nice large area on the sky, and any signals that you receive in that area will be detectable. It's also computationally cheap to do, and if you have the raw original data buffered, you can still do localization and beamforming post-detection. So this is another option. So just to illustrate this, I have an example here. What you see here are a series of waterfall plots like the one I showed earlier. This is from MeerKAT using the SETI, Reusable SETI system. You can see each strip across from left to right is the same piece of the band from each of 16 antennas. This is an example, a close-up of what one can see there. So you can see a signal there that's actually from Vela pulsar, an astronomical object which produces these repeated pulses. And incoherent sum would mean simply adding up all of these signals without any further processing, and the result is a higher signal to noise ratio in this image. So here's an example of what that might look like for all of those summed together. But in any case, SETI with arrays has a number of advantages. It's easier to reject RFI. So one does not have to do on-off observing as one does with the single dish radio telescopes. By forming multiple electronic beams, you can obviate the need for that, because you can look at different parts of the sky simultaneously and electronically. Another advantage is that smaller dishes are cheaper, so typically one ends up with a larger array with many more dishes, and actually perhaps even more collecting area than one would have with a single dish antenna. And this is possible because computing hardware has become cheaper and more capable. So the complicated steps of signal processing are possible for, are more possible. You also get, to some extent, you get your cake and are able to eat it. You have a large field of view, and you can get high sensitivity. So the size of the dishes allows a large field of view, and the fact that you've got many of them means you have a lot of collecting area. Your resolution is governed by baselines. That means the distance between dishes. So with a large distance between dishes, you can get high resolution. And all of this presents unique opportunities for commensal observing, which I'll speak about next. Another point to note is that historically, it's been more costly to build such array telescopes because the signal processing systems for this arrays had to be purpose-built with custom-built hardware and was sort of very unique to each instrument. Whereas nowadays, Ethernet networking allows reusable components and cheap general-purpose hardware, and also enables commensal observing. So I'll explain a little bit more about what I mean by that now, after introducing MeerKAT. So I'm going to speak specifically with reference to MeerKAT. So for those of you who are not aware, MeerKAT is a radio telescope located in a radio quiet reserve in South Africa, in a remote region of South Africa. Currently consists of 64 offset Gregorian antennas. You can see examples of them in the image on the right. You can see that the offset Gregorian design allows for unobstructed line of sight to the sky. It's offering UHF, L, and S band observing bands, and will be integrated with the square kilometer array in future. And there's more to come. There's the MeerKAT Extension project in 2023 with an additional 20 antennas, and the maximum baseline will be extended. So that means one can observe with higher resolution. And then ultimately, there'll be integration with the square kilometer array, which is an additional 133 antennas and greater baselines, and future possible expansion with neighboring countries. So Commensal SETI with MeerKAT is very possible and very powerful. So Breakthrough Listen has a Commensal SETI system attached to MeerKAT. It's named Breakthrough Listen User Supplied Equipment. It's one of a number of user supplied equipment projects. So this networked Ethernet capability that I mentioned before allows multiple users of the telescope to receive data at the same time. So that allows for Commensal SETI. So by that, I mean a primary observer will be conducting observations of whatever sources pertain to their science goals. And at the same time, another experiment could receive the same data, but depending on which data they've selected, they can see the whole primary field of view of the telescope and might be able to beamform on targets of interest within the primary field of view, which is exactly what the SETI program at MeerKAT BLUs intends to do. So in this image on the right, you can see an example of the telescope looking at a primary target of interest, which might be a pulsar. And within the primary field of view, there are targets of interest for SETI observation. And through electronically steered beams, we can look at those sources at the same time that the primary observer is looking at their source. So for the Breakthrough Listen system, it'll be entirely automated commensal observing. It'll make use of both the Incoherent Sum mode and beamforming with the goal of 64 simultaneous beams with a modular online processing pipeline, which I'll also speak a little bit about. And the goal is to observe more than 1 million nearby objects. So this is an example of the kind of Ethernet architecture at MeerKAT. So you have the antennas and the digitizers that turn the analog signal from the dishes into digital information, which is sent via an Ethernet network to the digital signal processing components, and also all the commensal and primary users of the telescope. You can see there are a number of others. Some examples might be FBFUs or PTUs, which look at pulsars and various other objects, but BLUs would be one of these user-supplied equipment systems, which is which I'll go into a little bit more detail next in this slide. So the kind of broad signal processing outline of the telescope is as follows. You have the signal from the antennas that's channelized into data that looks a lot like those waterfall plots that I showed earlier. And that's where BLUs will tap into the data because BLUs will run its own beamforming, will have its own beamformer so that it can form these 64 beams in the primary field of view. So this is a little bit more detail into what the Universe SETI system will look like. There's a metadata interface which will receive all the information about what the telescope is actually doing. And this is necessary so that the system can be automated so that it can handle all the different forms of primary observation. And then on the other side, the raw data itself, which arrives at an extremely high data rate, will be received by the kind of heavy processing system, the processing nodes. And this information will be integrated in this modular pipeline with the end result storage of candidate signals. So something to note is that the data rate is so high, it's 27 gigabits per second per antenna. This data rate is so high that we will not be able to store all the data that we receive. Instead, we'll have an online pipeline that can operate in near real time or real time and detect signals of interest and triage them in terms of interest and save them in so-called postage stamp regions. So if there's an interesting signal, it'll save that signal and perhaps some other data from all the antennas, and that will keep the data rate low enough that we can record those signals of interest without having to record the entire full bandwidth at that high data rate. Okay. Another thing that I wanted to mention is that what we're working on here is some parts of it will be reusable. So the interface with the telescope itself is specific to MeerKAT, but some of the latter stages, including the modular pipeline, will be reusable by other SETI systems. And I would also note here that other existing telescopes are being fitted with Ethernet-based commensal observing capabilities, such as the Allen Telescope Array and the Very Large Array. A little bit more on the modular pipeline. So the idea behind this is that we'll be able to rapidly try out different methods of SETI signal detection throughout the whole processing chain. Since we're not saving all the raw data, this is particularly important because we might want to try out different methods and compare them quickly. And so we'll have a variety of different options. The standard ones would be beamforming and a Doppler drift search. That is a search that looks for time varying, or frequency varying narrowband signals. And we'll also have the incoherent sum mode, and we'll also use various other machine learning methods which are being investigated, but are a little bit less mature than classical Doppler drift methods. And then ultimately there'll be some triage of candidates, and we'll save a certain rate of candidates to disk. Let's see. I included this slide to show what the physical system looks like at the moment. In fact, this is not even quite quite the full extent of it. There's even a few more machines have been installed since then, but this is one half of the breakthrough listen system. This can ingest the full band at L band and store 5 minutes worth of raw voltage data. On the left, you can see all the machines in pallets before they were installed, and that's the sort of traditional SETI flag of Earth, which was also 1.5 meters in width. So we were observing social distancing measures in place at the time. Another thing that I wanted to talk about here is how to conduct a targeted SETI search with a commensal SETI system. So since one has no control over where the telescope is pointing as a commensal user, one has to be ready with a set of targets that might appear within the field of view that you would want to observe. And as the objective is to observe more than 1 million nearby objects for 5 minutes each, which is 1 buffer's worth of data, we had to prepare a catalog of many objects over the entire sky, such that no matter where the telescope was pointing, there'd be objects of interest. So this list of approximately 26 million stars was compiled from Gaia data, which is a satellite and research program to catalog stars and their distances. This was compiled by former breakthrough listen intern Logan Pierce. And we also added other objects to the catalog. There's the Exotica catalog by Dr. Brian Lackey. There's a publication about that as well. And also nearby stars not available in the Gaia catalog. Some very bright and very nearby stars do not appear in the Gaia catalog because they, partly because they move too quickly or are too bright. This slide is the result of fairly detailed simulation of observing progress that we might hope to achieve. So this shows the number of stars in thousands that might be observed during a commensal search that uses a targeted beamforming. The processing time, these are very conservative estimates, and in fact, in reality, we may need much less time to process. But even in this case, we can see that in just 6 months, one might observe more than 400,000 stars through commensal observing capabilities in this way. And that's through targeted beamforming, and doesn't consider even the possibilities afforded by the incoherent sum mode, which will be conducted in parallel with coherent beamforming. So I think that's the end. Thank you very much. I'd like to point out that our code and data is available on GitHub and the Open Data Archive. The links at the top, and there are a few links at the bottom as well. But thank you very much. And if there are any questions, please, please go ahead.
Thank you. I see that Jill Tarter has a question, and then there are a couple in the Q&A as well. And I just want to remind everyone, feel free to add your questions to the Q&A, and I will be able to read them out. But I'm going to open up first with Jill.
Hi, Daniel. Great talk. Great talk.
Thank you.
As you're working with MeerKAT and this pipeline, have you figured out a way to, in near real time, when you have a candidate, go grab more data and reobserve it quickly?
Right. So the advantage of the approach taken at MeerKAT is that all the raw data for the past 5 minutes at least is stored for the full duration of processing. So the whole 5 minutes is available. But during that time, if the telescope is on the same pointing, the other bank of processing nodes will be observing the same region of sky. And so you could quite easily, if something is detected, flag that as a high priority object to observe and have it reobserved in the subsequent processing cycle, which would happen with the new data recorded for the 5 minutes after this first set of 5 minutes. So as long as it's within the same primary observation, that would be possible. I think it might become further processing and investigation is needed for sort of longer timescales, I think, since it is a fully commensal search.
So just a little politics. There's been no discussion with the other commensal observers or the primary observer that if you have a candidate and it keeps on being a good candidate, that you can ask that they not move the primary field of view?
To my knowledge, this has not a subject that's been broached, but I'm probably not qualified to speak on that. But yeah, as far as I'm aware, we completely commensal in that we just react to the current primary observation and have no immediate feedback loop.
Okay.
In that sense.
So super. How much of this is actually working, and when will it be fully working?
Right. So currently, the incoherent mode, an incoherent mode, a form of the incoherent mode, is operating. The fully automated commensal aspect of the system is also working. So the automatic procedure by which the system determines the current state of the telescope, where it's pointing, the form of the data, all of that, and then tells the processing nodes how to ingest the data and how to record it. That's also working. We have a number of people working on the Beamformer and some other aspects of the SETI search pipeline. And I believe there's a date in early January that's targeted for sort of full operational capability of the first stage, or the first beamforming stage, I should say.
Now, in what appears to be a continuation of this issue that Jill's raised, there is a conversation going on in the chat room between Bernie Vanderhoff and Marshall Eubanks. Dave, do we have the ability to have either Bernie or Marshall or both give us a sense of that conversation that's taking place over there?
Bernie can certainly unmute. If, depending on time, I could get Marshall, but maybe Bernie wants to say.
Maybe we'll let Bernie just summarize what's going on in the chat there. I think it's coming directly out of Jill's insightful question.
I actually thought I was sending it through to you, but not to Marshall. So all I was saying was that there is director's discretionary time. And I'm sure if we came up with a good candidate for a SETI signal, it would be possible to get director's time to follow up that signal. I can't commit the director, obviously, but I'd be very surprised if he weren't prepared to do that.
And then I can just jump in and summarize. I think most of you can see what Marshall's written there, but just pointing out there are 2 next generation VLBI projects presently ongoing that might be of interest to Breakthrough Listen, and some of the details are there now. Jill, did you want to have a follow-up question there?
No, just good
You're
luck.
Good? All right.
Good luck. It looks wonderful.
Then I'll jump
Thank you very
over
much.
chat then and just read you some of the questions that are there, Daniel, in the
Sure.
remaining time that we have. One of the questions that's asking, does blues do trial? And you have to forgive me, this is not my world, so I will both mispronounce and probably make a mess of this, but it seems to say, does blues do trial de-dispersion in the coherent beam forming to detect fast bursts that could be SETI related, or is that exclusively done by the Trampum Thundercat USEs?
Okay. So, I mean, for the SETI search pipeline, there's the Doppler de-dispersion search that looks for these time-varying signals, but we're not doing. I'm not sure if I understand correctly. We're not doing like pulsar searching or any kind of folding approach. It's entirely to look for these time frequency varying narrowband signals that might be indicative of extraterrestrial origin.
And then there's a second question related to blues, which asks, blues, does it not have a correlator? And that is from Marshall Eubanks.
Sorry, Delius, does it?
Does not have a correlator? Question mark. SETI. Okay, yeah, go ahead.
Right. No. So as part of the there will be a correlator as part of the beamformer, but we can also use data from the MeerKAT correlator itself.
Great. And we do have about a minute remaining, so actually I'm going to jump in and ask a question. As an isotope geochemist, one of the fascinating things about isotope geochemistry is that we are all cross-correlated against the same standards, which are kept and are archived in Vienna. So every lab around the world undertakes the same prep, the same cross-check, the same Robins. We do multiple 5-team laboratory cross-tests and cross-calibrations. Now, all of that's very simple to do compared to what you do. So it really, in some ways, is a very false analogy. But I'm nonetheless curious. I come from a community that spends a lot of time doing what would be called cross-calibration developing. And you mentioned this as well. And indeed, there was discussion of this yesterday. You mentioned criteria for detection, frameworks for detection development. How is it that your community goes about achieving that? What are the mechanisms and what are the current thinking about how the community comes together around those issues, or do they?
Do you mean in the sense of if there's a candidate signal that seems very interesting, what standards would be applied to determine whether it is really a technosignature or not?
Well, you talked quite a bit about that, but I'm wondering about community around that. Do different communities and different labs have different sets of criteria? Is there a topic of discussion for developing more universal criteria that everyone agrees on? Just what's the state of play, just because it was such an interesting set of discussions yesterday?
Right. So I think there's some of it might be generally accepted that I'm hesitant to speak for the community here, and I would also pose this question to others such as Jill Tarter and Jason Wright, who spoke yesterday. But I think there's certainly some things that I think would be quite commonly accepted, such that if there's a signal of interest, it should be reobserved. There should be follow-up observations. I think there's certainly a set of criteria that one might apply to consider to see whether or not a signal is a technosignature or not. And some recent publications have put quite a lot of thought into this. For example, in fact the paper that I referenced the analysis was led by Dr. Savir Sheikh. She has given a lot of thought in that paper and others to this exact topic. Yeah, I think there's a.
Thank you. Yeah, that was actually what sparked my question. I was curious to know how widespread, how community-driven, what are the ways and mechanisms by which that kind of thinking is being developed. It was a very nice exposition and examples that you gave us there. Thank you.
Right. Yeah. And maybe one other thing that that I should mention is that this, the data and the tools by which the data were processed are also made entirely open source and available to others once detection has sort of been verified, I would say, and that gives everybody an opportunity to investigate and compare results.